Welcome back, everyone. So we're going to be starting our next unit, which is mainly Chapter 10, but we do have these two sections from Chapter 9 covering arc length and surfaces. So similar to volumes, arc length and surfaces of revolution, we're going to use integration to determine both of these. So the arc length is just going to be the measure of the arc. So we're going to be measuring the length of an arc that has curvature as opposed to like a line segment. So we can't use the Pythagorean theorem to find arc length arbitrarily, but we're going to use it actually with the limiting process to determine the arc length of a curve. And then we're going to add that on to developing a way to find surface area of a solid figure that we're going to, again, rotate in the plane in order to get the surface area of some shape. So we'll start with arc length. So with arc length here, we'll look at the following curve f of x. So we've got some arbitrary curve in space. We can say that it's between two values, so we'll make it finite length. So between a and b, let's say. And so what we're going to do then in order to find the length of this curve is we're going to break it up into some smaller pieces. All right, so we're just going to choose, we could make them all the same length. We can make them all different lengths. Doesn't really matter how we choose to do it. But let's suppose that maybe we're choosing the same length all the way across. That way we'll get kind of a uniform shape as opposed to kind of a mixed shape. So we'll call each point, let's see, we could call them, let's say P0, P1, P2, P3, dot, 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 up to some Pi minus 1, Pi, so that's going to be somewhere in between, and then we'll have P sub n minus 1 and P sub n. So we're going to have from P0 to Pn be all these points, and what we're going to do is we're going to measure individually all those distances. All right, so we're going to measure all the distances between any two adjacent points, P sub I. So we'll just note here, if we did say P0, P1, so we can just use kind of geometric segments to represent that length, that we would find by using just the Pythagorean theorem, right? Just the distance formula. So we would get, and we'll assume that P0 is like x0, y0, where x0 is also equal to a by our picture here. But we'll get x sub 1 minus x sub 0 squared, and y sub 1 minus y sub 0 squared, quantity squared. So that's going to be each individual length is going to look like that. And we're just going to generalize it and then start the limiting process. So let's go ahead and do that. So by our picture here, we're going to describe that distance process as kind of a general expression. So let P sub I minus 1 P sub I be the distance between those 2 points. Then that is going to be the same as x sub I minus x sub I minus 1 plus y sub I minus y sub I minus 1. Oops. Quantity squared. And so this is going to be true for any 2 points that we choose. So then now that we've, made this arbitrary point I in the middle, we can now take the sum of all of these possible ones. So we'll just note that I is just between 0 and n. So then if we take the sum, as I goes from 0 to n, of P sub I minus 1, P sub I, right, the sum of those is going to represent an approximation of our arc length. So now this is going to be an approximation of the arc length. But we want, of course, it to be better than an approximation. So what we're going to do is we're going to let the number of points approach infinity so that we have an infinite number of little minuscule lengths that we're measuring that is going to end up giving us the exact measure. So let's go ahead and think about what we would do for our function here. So we'll just note that p sub I and p sub I minus 1 can be represented with x sub i's and y sub i's. So from above here, what we'll note on the side here is that x sub I minus 1, we could simply call delta x if we wanted to, right? That's just the horizontal distance, and then y sub I minus 1 is delta y. So it's the vertical difference between those 2 points. So delta x, delta y. So another way then that we could write this is that this is going to be the sum from I equals 0 to n of the square root of, now again, I've kind of said we'll make the subintervals the same, but we could also just kind of make them arbitrary as well. So instead of x sub I minus 1 minus x sub I minus 1, we'll just call that delta xi squared and then delta yi squared. But again, we can make them uniform length, equal lengths. Okay. Now, when we take the limit of the Riemann sum, what we should know is, as n goes to infinity, delta x becomes dx, and delta y becomes f prime of x dx. So the delta x one should be obvious. The delta y one maybe not so. So let's again remember that if we have y equals f of x, then dy over dx is f prime of x, which means that dy, why don't we write it that way first? So delta y becomes dy as n goes to infinity, which is equal to f prime of x dx. So dy equals f prime of x dx here if we write it in that integral form or differential form. Okay. So let's go ahead and take the limit of our Riemann sum. So thus, the arc length of f on the interval AB is given by the following. So we have the limit as n goes to infinity, the sum of I equals 0 to n of the square root of delta x squared plus delta y squared. And what that's going to give us is the integral from a to b, the definite integral, of the square root of dx squared plus dy squared, which, as we mentioned before, is f prime of x dx squared. Now we can clean this up a bit. We can factor out a dx squared from both terms and then square root it, and then we'll get our normal integral form here. So if we, again, factor out the dx squared, we'll be left with 1 plus f prime of x squared. But again, that's all being square rooted, which means that we'll get the integral from a to b of the square root of 1 plus f prime of x squared dx. And there's our arc length formula. And again, all we're doing here is using the Pythagorean length and taking that limiting process using the limit of a Riemann sum with our differentials. Okay, so we can note that here. So we've got integral a to b square root 1 plus f prime of x quantity squared dx. And we could have done the exact same process by reversing our coordinates here and doing it as a function of y. So the only thing, again, that's going to change if we're doing it as a function of y is we're going to change the variables that we're using. So we get the same expression just as a function of y. And you'll kind of have to figure out which one you prefer to use, but there will be typically pretty specific ways that you can identify which one you want to use. Okay. So we're going to skip the examples for a moment, and we're going to go to surface area. So all right, so for surfaces of a revolution, we're going to use arc length with it in order to determine that. So if we look on the left here, we've got the case where we've got, say, maybe a finite number of subintervals. So we're going to break our curve up into 4 pieces here. And then what we're going to do is take each piece, take the arc length between them as an approximation, so just that Pythagorean length. And then we're going to rotate that portion of the length around the x-axis. So we're rotating about the x-axis to get our surface. And so what we get is this sort of trapezoidal shape that we're rotating, right? So if we had a constant function, it would be a cylinder. But in this case, we've got a curved function. So we don't get a cylinder because our top and bottom bases have different radii. So we get 2 different bases for our shape. So what that is going to look like is something like this. And what we call this shape that has this trapezoidal cross-section is called a frustrum. All right, so a cylinder is a frustrum with equal radii for the bases, but in general, we're going to assume that it's some uneven leveled trapezoidal cross-sectional solid. So for the frustrum, if we want to find the surface area of a frustrum, let's think about what it would look like for a cylinder. So if we have a cylinder, and again, we're only talking about the area around the circular, the cylinder, not including the top and bottom base. So that's going to be the distance around, which is the circumference of the circle, times the height, right? So there's kind of 2 pieces there, circumference times height. So for our frustrum, it's going to be very similar. Oops. So for our frustrum, we're going to have 2 pi r times, now it's no longer height, it's what we call the slanted height, L. And the way that we get r, since we have 2 different radii, maybe call this r1 and this r2, r is going to be the average of those 2 radii. So we take the average of the 2 radii in order to get the surface area. And so what we get is this expression, which is very similar to our cylinder with a slight difference here. Now, this averaging value is not going to be very important to us because we're going to consider an infinite number of subintervals. So we'll have an infinite number of these really small frustrum shapes that we're calculating the surface area of. So we don't have to worry about taking the average because we'll take any point in between, and if we shrink it small enough, that will become the correct radii. And then the slant height, well, that's just all of our P0, P1s, P1, P2s, just our arc lengths. So the slant height is going to be represented by the arc length expression. So let's go ahead and look at then what our general formula is going to look like. So for any particular frustrum, let's say we wanted the surface area of P0, P1, then in order to calculate that, that would be 2 pi r times L, right, for the particular subinterval. But how would we choose the particular values? Well, we can look at what the radius would be here for this figure. So let's go ahead and do that. So I'm just going to draw the x-axis through here, which is going through the center. So maybe that will be our r. And so we can call that r of x sub, maybe we'll just call it x sub 0. So that's going to be the radius on that first subinterval. But that's really just f of x sub 0. That's just going to be the function itself. And then if I look at the slant height, well, the slant height is just going to be the distance between those 2 points, all right, which we can write with the square root expression. So we'll note 2 pi RL is going to be 2 pi f of x sub 0 times the square root of 1 plus delta y squared. So again, from our formula, we could put, delta x squared plus delta y squared. So if you wanted to do that, you could as well, and then we would simplify further. But for any particular frustum-shaped portion that we're looking at, the surface area will look the same for that particular location, and you could call it, delta y sub 0 if you wanted to. So what we're going to do is we're going to take the sum of all of those, of course. So what we're going to get is the sum I equals 0, or maybe we'll just do I equals 1 to n. Well, we started at 0. So I equals 0 to n, and we'll have 2 pi f of x sub I times 1 plus delta y sub I squared. And then we'll take the limit as n goes to infinity. So we'll take the limit of our Riemann sum. Which again is going to give us the definite integral from a to b. So again, whatever our domain length is given will be a to b of 2 pi f of x, the square root of 1 plus f prime of x squared dx. Oh, I guess we should add a delta x on the outside. Sorry. If we do delta x squared plus delta y squared, we can rewrite it in this way. So we end up with this formula. And note that the radius can change if we rotate about a different axis, but for surface area problems, you're pretty much going to be rotating about the x or y axis exclusively. Not always, but it will happen for most of the examples that you see. All right, so let's go ahead and generalize this for our notes here. So the surface area S is going to be the integral from a to b of 2 pi, we'll call it r of x for that radius times the square root of 1 plus f prime of x squared dx. And note that this is typically simply just going to be your function, but we'll assume that there's other axes that we could be rotating about. So that radius could shift location from where it's at. And then for our vertical representation, if we have functions of y, where we're measuring distance from the y-axis, then it would just be r of y times the square root of 1 plus f prime of y squared dy. Oh, sorry. Yes. And then again, this will typically equal whatever f of y is in most cases. So we've got our surface of revolution formulas, we've got our arc length formulas, we're going to use them together to work the remaining examples out. So I'll put that in our next video. We'll start working on some of those examples together. So if you have questions on these, definitely send me an email or come by the office hours. Otherwise, until I see you next time, take